All right, section 4-8, remember, is on the derivatives of implicit relations. Talking about implicit differentiation is the term that we use to describe this, and the objective was, given the equation of an implicit relation, find the derivative of y with respect to x. Again, that implicit relationship term there is referring to an equation that's not solved for y. Explicit means it is solved for y, implicit means it's not. All right, let's take a look at just a couple of examples here. Example 3 on page 171 there says if y is equal to x cubed, or excuse me, y is equal to x to the 7/3, it says prove that the power rule, which you proved it for integer exponents, gives the correct answer for y prime. If you recall back in chapter 3 when we learned the power rule, we used the binomial theorem to be able to expand that thing, and that only works if you have an integer exponent. And in this case, of course, we got 7/3 as the exponent, so we want to check to make sure that it still works if it's even if it's a rational exponent like this. We've been using it like it does, but this is kind of a way that we can verify that in fact it will work. And so what they want you to do is to rewrite this as an implicit relationship instead of an explicit one. And we're going to do that by cubing both sides of this. So on the left side here, we're going to get y cubed. On the right side, of course, I multiply exponents here. 7/3 times 3 gives me x to the 7th. So you see I get rid of the rational exponent there. It's now an integer exponents that I'm working with. So I can actually use the rule I already know works for integers to help me see if it works for rational exponents. So now let's take the derivative of this thing with respect to x. So on the left side here, again, follow chain rule as you do this. So it's 3y squared times the derivative of y, which is y prime. Derivative of the outside, substitute in the inside, times the derivative of the inside. And that's equal to, on the right side, derivative of x to the 7th is 7x to the 6th. We're trying to find out what y prime is equal to, so let's solve this for y prime. We get 7x to the 6th over 3y squared. The only thing I don't like is that I started out with y by itself, there, y, or solve for y, I should say, as a function of x. And I end up with a derivative here that's got x's and y's mixed together. So let's see if we can get this in terms of just what x is equal, or just x's instead of both x's and y's. And I think we can do that if we do a substitution here. For y, we said y originally was equal to x to the 7/3. So I'm going to replace the y there with x to the 7/3, and we're squaring that y. And let's see what we end up with. I'm going to go ahead and write the 7/3 out front. That's just a coefficient there. And we have x to the 6th over. I'll end up with 14 over 3 when I multiply the 2 times the 7/3. So it's x to the 14/3 is what we end up with. And of course, my rule here to simplify this, I just subtract the exponents of these two when I'm dividing these two powers with the same base. So this is equal to 7/3 times x raised to the 6 minus 14/3. Now 6 would be the same as 18/3. So 18/3 minus 14/3 would give me 4/3. And there we go. That's actually what the derivative that we would get if we just simply followed power rule on this thing. The 7/3 would come out front, and we'd subtract 1 from the exponent to get 4/3. So in fact, our rule is correct there. It works for not only integer exponents, but also for rational exponents, our power rule, that is. All right, let's take a look at one last example here. One more of these derivatives of an implicit relationship. They want us to take the derivative of this and find out what y prime is equal to. So let's take the derivative of the natural log of x times y plus y squared is equal to the sine of y. All right, so on the left you have a sum of two functions, so follow your rule for the derivative of a sum. You take the derivative of the first function, which is a composite function, so we're going to follow chain rule. Chain rule says you take the derivative of the outside function, which is 1 over x times y. It's derivative of the outside, substituting in the inside, times the derivative of the inside. Now the inside function is a product, so I got to follow product rule. Derivative of x is 1 times y plus x times the derivative of y, which is y prime. There's the derivative of natural log of x times y. We're going to add that to the derivative of y squared, which is 2y times y prime, again following chain rule as you take that derivative. And on the right side, again, you got a composite function, so follow chain rule. Derivative of sine is cosine of y. It's derivative of the outside, substituting in the inside, and then multiply by the derivative of the inside, y prime. Now, what I want to do is solve for y prime, so I see that I have a y prime sitting inside of these parentheses. In fact, we'll go ahead and underline all of our y primes that I want to eventually combine here. Oops, I didn't need that parenthesis at the end. And so in order for me to combine all those, I first need to distribute this 1 over x through the parentheses so that I can then get all the y primes together. So let's do that first. So when I take y over, 1 over x times y, I guess I'll write it as y over x times y, and we can simplify it here in a second. And when I do the same thing for the next term, I'll get x times y prime over xy. And then we've got plus 2y times y prime. And that's equal to the cosine of y times y prime. All right, so a couple things will cancel out here nicely. The y will cancel out over here, and the x's will cancel out here. And so we end up with the following. We want to get all of our y primes together and all of our other stuff, which I guess we only have one term that doesn't have any y primes in it, on the other side. I'm going to keep all of our y primes on the left. I'm going to rewrite this first y prime term as 1 over y times y prime. That's the same as y prime over y. Plus the 2y times y prime. And we're moving the cosine of y times y prime over here, so that's a minus cosine of y times y prime. And that's equal to, we're going to move the only term that doesn't have y primes. It's the first term that we had on the left side. That's just 1 over x. It's not just x. Remember, that's 1 over x. The x is in the denominator there. And factor out the y prime on the left side. So you get 1 over y plus 2y. Oops, and it's minus the cosine of y. And that's equal to 1 over x. All right, and finally, the last step of this is to divide by this factor that I have over here on the left side. So I have y prime is equal to, I guess there's a couple ways you could write it, but I'm going to write it as 1 over x divided by all of this stuff. It's 1 over y plus 2y minus the cosine of y. And there's certainly some things I guess you could do to rewrite this a little bit. I don't know that I would suggest it, but you could definitely move the x that you have in the numerator, that 1 over x, into the denominator if you wanted to, but I might suggest you leave it in this form. If you wanted to go one more step with this, realize you can rewrite this as 1 over x times all of this, 1 over y plus 2y minus the cosine of y. And I guess if you wanted to go even further, you could distribute that x through there, but I'm going to stop right there. There's the derivative of our function.